Just run through quick using the computer to verify what we've just done. And I went ahead and rather than, and again, I think that this is an important thing for you to consider is these are too easy to find just the derivatives of by hand. There's no reason to use SymPy in the machine to solve these equations. It's faster and easier to do it by hand. So that's okay. I don't need to verify that. It wasn't very complex. I trust you feel the same way. So we have our functions, their derivatives, and their second derivatives defined. If we look at x, f of x, we have this. We found that its critical value was 0. So if we plug that into the second derivative, we get negative. That's for g. ddf. Our function f that we have plotted here. That's positive, right? So that's concave up. And we have a minimum at 0 because we knew that that's a critical value. And sure enough, that's what we see when we look at the graph. All right, same thing with g. We just want to look at a plot and evaluate the second derivative at its critical value. So here we have g. All right, that's what g looks like on this same interval. And if we evaluate the second derivative there, sure enough, we get a negative value. It's concave down, so that must be a maximum. Okay, and that's the idea of the second derivative test. Now, let's look at one more example with the function 5x cubed minus 3x. Same idea, we want to evaluate the function, its derivative, find the critical points, use them in the second derivative. So by hand, we end up with the first derivative is 15x squared minus 3. The second derivative is 30x. All right, if we set this equal to 0, we would add 3 and divide by 15. Again, we get that x squared equals 3 over 15 or 1 over 5. So x is plus or minus the square root of 1 over 5. And then we can just plug in here. Now, if we plug in positive the square root, this is going to be positive. If we plug in negative the square root, this will be negative. And voila, right? So again, if this is positive, we know that a graph is concave up. It looks like this. So it must be a minimum. If it's negative, it's concave down. So we must have a maximum. And sure enough, that's what we saw earlier when we plotted this, right? Just to verify, we can define our function. Evaluate the second derivative, or define the second derivative. Call this ddf. And that was 30x. And if we want to evaluate that, we could say that's at np dot square root of 1 over 5. It's positive. Okay, and same thing at negative np dot square root 1 over 5. It's negative. And again, if the second derivative is positive, we have concave up, and it's a minimum. And if it's negative, it's concave down, and it's a maximum. So just even to be for sure, let's plot these between negative 1 and 1. And we'll also plot those points, right? So this is np dot square root 1 over 5, and f of the square root of 1 over 5. Make that a red O. Okay, and then we'll just do the same thing, except at negative. So sure enough, at negative 1 over 5, it's concave down. So we have a maximum. Square root of 1 over, positive square root of 1 over 5, it's concave up. So we have a minimum.